Good afternoon, ladies and gentlemen. It is my pleasure to introduce this conference on the ITER project. We have with us Dr. Bernard Bigot, who is a friend and the Director General of the ITER organization since the 5th of March 2015. He has a long and distinguished career, Bernard. I will not go in all the details. I just want to say that he has followed fusion consistently since 2003, when the discussions started to heat up on where to site this worldwide extremely important project. Before he has headed the CEA in France for 2 terms and has been in various advisory posts of the President, of the Prime Minister, and so on and so forth. Bernard will bring us through the ITER projects, its status, its value for fusion, for Europe, for energy. So Bernard, with these words, the floor is yours. Thank you very much for having accepted to address us this evening.
Thank you very much, Massimo. I am deeply honored to have been invited to make this presentation in front of the prestigious audience of the Bridge Forum Dialogue. And it's my pleasure really to introduce you to the ITER project and more broadly to the fusion. You have on the screen, indeed, photos of the work site, the ITER work site, as it is now near Aix-en-Provence in France, is a very large platform, nearly 50 hectares, where in the center you have what we call the tokamak building, which will host the fusion we expect to be able to develop. And I do believe that this project is much more than just a research international program. It is, we hope, the way to open a new energy future. So, it does not work. Okay. Always the technology, as you know. Okay, so let me introduce the issue. I do believe that the hydrogen fusion could contribute to resolve what we call the energy dilemma, which is fueling civilization with sufficient clean energy without impacting the planet. And as maybe you know, the world has developed during a millennium just relying on renewable energy. It goes on this way until the end of the 18th century, where people rely only on the solar energy because nearly all the renewable energy is coming from solar energy. And due to the fact that solar energy has some specificity, which is diffuseness, you need a lot of space in order to collect the solar energy, either for growing the plants with the photosynthesis or for collecting directly the water flowing from the rain. You need a lot of land. And so is why the world population was limited below 1 billion of inhabitants. And the expectation of life was quite limited also around 35, 40 years old, because people has to work hard to get the energy. Indeed, we are now facing the challenge that after we have discovered the fossil fuels, now the world population is beyond 8 billion of inhabitants and maybe nearly soon, 10 billion. And we need to provide sufficient energy without any impact on the climate and the planet. As you know also that electricity is a primary vector of social and economic development, and indeed the world is facing some inequality since we believe that nearly 1.6 billion of humans still are not connected to the grid. And second point, we would like to mention that this energy dilemma is even larger than we could feel if we consider that the global energy consumption has grown 50% since 1973, and it is expected to go 60% more by 2030. So it is this that this research program tried to consider, and the goal of ITER is a long-term sustainable energy supply for the world jointly with renewable energies. The main requirement is to try to what we call decarbonize the energy production as it is now, since the current status is more than 80% of energy consumed in the world is from fossil fuels, despite the best effort we are doing. And 65% of the electricity production is relying on this fossil fuel consumption. And the hugest task ahead is how we will transit from the situation where we are now to a situation where we will be able to reduce drastically the consumption of fossil fuel during this century. As I explained, our goal is to contribute to sustainable clean energy. And we believe, as physicists, that sustainable clean energy sources will come from well-known physical phenomena. Renewable, as I explained, we need to develop them as much as we can. And it's very impressive, the recent progress due to innovation, which has reduced drastically the price and increased the performance. But there is limitation. The limitation is clearly the intermittency. Maybe we will develop some way to store better the energy, but anyhow, intermittency will be there, and to store is energy costing. And the second is a low power density, what we call diffuse nets, which are nearly not suited to concentrated demand of industry, which required large, massive production, reliable production, as well as with mega cities. And I'm sure all of you know that now more than 80% of the world population is living in cities. A second option, which will not produce impact on the climate and reduce impact on the environment if everything goes well, is nuclear fission. When we break down heavy nuclei as uranium, it clearly offers clear advantage. I have been working in this field for many years, and I do believe that if it is well organized, if it is well managed, the advantages are really great. But as you know, there is also some risk, and these risks are perceived by the population, and so about the safety and as well as waste management. I do believe that nuclear fission is good for the transition, but it is not a long sustainable technologies due to the concern I explained, but also to the limited amount of fissile product. Mainly, as you know, the only natural fissile product as it exists now, it is uranium, natural uranium, and there is not so large amount in the world. So we have to look back to another natural phenomena, which is fusion, and I do believe that it is a promising solution. Promising because there is a quite significant advantage of what I call hydrogen fusion, fusing the hydrogen. It is first a way to produce massively in a predictable way baseload power, which could be complementary to renewable. Why complementary? Because you could switch in and switch out depending when the renewable are producing or not. So it is quite important that these two technologies are not opposite, they are complementary. The second, it is intrinsically safe because, as we will see, we have in the devices, in the power plant, only a very small quantity of fuel, and in anything is going wrong, the reaction stops. It is a counterpart of the very challenging technologies, but if we are not fully compliant with the nominal parameter for good functioning, reaction stops. There is no storage of energy. There is only a flux of energy. And it does not impact the environment and climate because we are just producing helium, which is, as you know, quite non-chemically active materials and neither radioactive materials. And the last, maybe not the least, we have nearly virtually unlimited fuel, which we call raw material, to provide the needed fuels for the fusion production, which is water and lithium, because the formal chemical equation is just deuterium, which is a special brand of hydrogen coming from water, plus lithium, and you will produce only helium. No greenhouse gas emission, as I said also. We will have some radioactive waste, but they are quite limited in amount and also of activity. So it is with this advantage that everybody is considering this famous hydrogen fusion as it is demonstrated for billions of years in the universe. I am sure you are aware that what powers the sun and the star is hydrogen fusion. The source of all heat and life on Earth is coming from this phenomena. So what is the phenomena? The phenomena is quite simple. When you have two hydrogen nuclei, if you try to make them coming closer, they will be repulsing each other due to what we call electrostatic repulsion. But if you make them getting so close, what we call the subatomic dimension, you enter with a new type of forces, which is what we call the near close fusion phenomena, close fusion, which attract the nuclei and make them producing a new nuclei. It's what we call the nucleogenesis. The universe has been working like this, and it is what makes the nuclei stable. It is this type of very nearby energy phenomena. The challenge is to be able to recreate on Earth this phenomena, and this phenomena is directly linked to the equation that the famous equation that Einstein discovered, that when you are fusing some material, you will have a reduction of the global mass, and this reduction of the global mass will produce a huge amount of energy. Clearly, what's happened in the star and the sun is because at the center of the sun, you have a very what we call hot plasma of the order of 15 million degrees, with a density of nearly 100 times the density of steel. And in this physical condition, the gravitational forces are forcing the nuclei to get as close as I mentioned before. We could not afford to have all the mass of the sun, which is nearly 300,000 times the mass of the Earth on Earth, and is why the physicist has to develop some alternate option to force the hydrogen nuclei to get so close they will fuse. And what is possible is to use what we call the magnetic forces. In this condition, we will be able to have a very low density plasma. It is a density which is nearly 1 million less than the density of the atmosphere. And in this condition, with the magnetic forces, you will be able to accelerate the hydrogen nuclei in such a way they will achieve a very high speed, which is equivalent to a temperature of 10 times the temperature of the sun, 150 million degrees. And when they collide, they will fuse with a very high efficiency, and as in the sun, produce an helium nuclei with 5 times more energy than the energy of the collision, and a neutrons, which is 20 times more energy than the energy of the collision. It means that indeed, when 1 gram of hydrogen fuse is equivalent of 8 tons of oil immediately burning. It is a factor of amplification when you move from chemical transformation to nuclear transformation it is a factor of 1 million more energy. So it is this phenomena we are trying to use. And for doing that, we will need to have a strong magnetic field. If you remember your very early physics course when you were at school, you remember that magnetic field is creating magnetic lines. And if an electrical particle is nearby this magnetic line, it is trapped by the magnetic line and it spins around the magnetic line, continuously accelerating in such a way that if you have a very low density, you have enough space to reach the appropriate speed. As you understand, the magnetic will in some way trap the fuel, which will be prevented to get close to the wall of the vessel where you will be operating. And so you will be able to have what we call a self-burning plasma using the helium, which will be trapped as the hydrogen nuclei by the magnetic line, and we will transfer its kinetic energy to the energy of the fuel you are feeding in, the plasma. And so when you will have the same temperature for the helium and the hydrogen, you will suck out this helium because otherwise it will reduce the yield. And the neutron will escape from the magnetic cages and it will hit the wall of the vessel and it will transfer its kinetic energy as a thermal energy, the same as a silver bullet, I will say, will hit a steel plate and will fuse. So it is this concept that the Russians developed in the years 1950s, and on this basis that we are now working. And the principle to collect the energy is quite simple. We will have water flowing within the vessel wall, and we will produce steam, and the steam will be able to operate a turbine and produce electricity. So it is on this principle and with the advantage I mentioned that in November 1985, at the Geneva summit, President Reagan and Secretary Gorbachev announced they launched an international research project for the benefit of all mankind based on the demonstration of hydrogen fusion. It was quite a long development because during nearly 15 years, in the US, in Europe, near Garching, in Germany, and as well in Japan, a few hundred of technicians, engineers, scientists have developed the design, and by 2003, as Massimo has explained, the design was considered as mature enough, and so we launched the discussion in order to fix the governance, the cost sharing, and the localization. Negotiation ended up, and in November 2006, the ITER agreement was signed in France at the Élysée Palace under the auspices of President Chirac at this time. We start in 1st of January 2007 on the ITER site. We need to make quite a large transformation of the site to get a very flat platform. And it was ready by 2010 and the project started. And now you see how largely filled is the platform. The project indeed, it is linked, as I will explain in a few minutes, need size. Without sufficient size, you will not be able to produce a net output of energy. You will observe the fusion phenomena, but not having a net energy production. So is why all these partners, the 7, and you recognize certainly the European flag, have agreed to join their best effort in order to be able to make the clear demonstration. And now, as you see, all the partners are united in a common cause to transform our energy legacy using fusion. What is a ITER mission? It's very clear, is to demonstrate that the scientific and technological feasibility of fusion power for peaceful purpose at industrial scale is reachable during this century. It is to produce what we call a burning or self-heating plasma. Still, you will need some energy in order to heat up the plasma on a continuous basis when it is a steady plasma, but it will be quite reduced. And the mission, the goal, is to achieve a yield of over 10, which means that the thermal output will be of the order of 500 megawatt, while we are just feeding in the plasma 50 megawatt of heating power. So here is an image of what we call the tokamak with a big box around the vessel. This box is named a cryostat. It's 30 meter diameter, 30 meter high, is to preserve the cold temperature that is needed for the magnetic cages. And so how it works, so we will inject in the vacuum vessel chamber. The chamber is of the order of 1,800 cubic meter, only 2 grams of hydrogen. The gas will expand in the whole vessel. We will make what we call an electrical discharge, okay, in such a way that we will create a plasma, the same phenomena you have in maybe the bulb in your house, if you have a plasma bulb. And immediately, due to the fact that the vacuum vessel is embedded in a magnetic cages, they will accelerate the hydrogen nuclei, and they will heat up. It will heat up until maybe 40, 50 million degrees. It's not enough for the self-sustained fusion. So we need some extra heating with, for example, electromagnetic waves and some other way to proceed. And rapidly you will reach the 150 million degrees, and you are now able to have the plasma running and in a steady state. So the challenge that I say is how we could do that. We will do that with the magnetic cage. I will explain in a few minutes. So just to repeat again that size matter. The world record now is indeed a European world record on the joint European Taurus, which is now in UK, where in 1997, they have been able to produce 16 megawatt of fusion power resulting from the fusion of the hydrogen nuclei, but they had to feed in 23 megawatt, which means that the yield is below 1, 0.7. And they use a plasma, the volume was 80 cubic meter. In ITER, the volume of the plasma will be 10 times larger. We will doubling the heating power for having a burning plasma. And indeed, we will get 30 times more energy than in the jet. So definitively, it's not just a dream of a physicist to need to have a large installation. It is because the physics required it. There could be some improvement, but as soon as we are not able to have the time for acceleration and the confinement of a large volume of plasma, the yield will be too low. As you see again on the right side of the slide, it is an image of what we call the tokamak. It's like a cut of a fruit. You recognize in orange, the vacuum vessel, which is a torus. The vacuum vessel has some blanket which will collect the neutrons, and the water will flow in the double wall of this vacuum vessel. And this vacuum vessel is embedded in the magnetic cages I mentioned, which is made up of 18 vertical coils, 6 horizontal coils, and a central coil. And you have to understand that we will have here the most extreme difference of temperature that ever happened in the world. In the middle of the vacuum vessel, like a torus, you will have 150 million degrees. The temperature of the vessel will be 200 degrees with the water in. and the coils will be at a temperature of minus 270 degrees, nearly the zero, absolute zero. So it is quite a challenge to be able to manage this extreme condition. And in order to preserve, as I say, the low temperature of the coil, we have enveloped all these things in a cryostat. The major issue for having fusion working properly is to be able to assemble and operate a large magnetic cages. Maybe you see at the bottom of the slide the small persons which give you the feeling of what is the size of the cage. The size of the cage is 20 meters high, 20 meters large. It is like if you have a 7th floor building, and you have to imagine that the magnetic axis of this cage, made of this all these different coils, has to be positioned with a precision which is below 0.5 millimeter with the geometrical axis of the vacuum vessel. The reason is easy to understand. The electrical particles, the nuclei, will circulate at very high speed in the torus. And so if the trajectory of the nuclei are not perfectly fitting with the shape of the vessel, they will hit the vessel and get out of the magnetic cages. So it is this a challenge we have to deal with extreme precision and very large dimension. So, as I explained, the 7 members, and you recognize them, agreed to work together, but they also considered that hydrogen fusion could be a real breakthrough for the world, contributing to the world energy supply in a very innovative way. And so they decide that they would like to demonstrate that their industrial champion are able to manufacture the very challenging component with the requirement I explained a few minutes ago. And so they decide they will provide in kind the various components to the ITER organization, which is indeed the operators of the facility, which is in charge to validate the design and install the component and also start the commissioning and operation. But all the components are provided by the various what we call ITER members through what is domestic agency, which is a legal unit which are able to receive money from the government and pass industrial contract. And the ITER agreement, it has been agreed that all the ITER members will contribute of the order of 9% if they are non-European and Europe 45%. Why? Europe has accepted because, you know, there is quite a large economical benefit which is provided by the support of the other members while it is in Europe. So it is on this basis that the ITER agreement work on. It is not the simplest way to manage a large industrial project, but I do believe it was a prerequisite and we demonstrate it is manageable. So we have a very strict challenge. When we start in 2007, in some way it was a dream. People feel that it will take maybe 10 years after the site is ready for starting the project in 2010 in order to complete the construction, and maybe 5 more years to eat up until the target of getting 10 times more energy that you feed in the plasma. After 7 years, everybody realized it was a dream, and we have to review the program. And in 2015, 2016, we set up a new schedule. And since that time, we have been moving on and on, passing through the various milestones. And as you see on this slide, indeed, some of the components are already on site and being assembled. but most of the challenge is still to come, since in 2021, 22, 23, all the main component has to be on site. We are moving. Now, despite the COVID-19 pandemic, the project has made steady progress and is nearing 75% completion of total construction through first plasma. Since 2015, every year we were progressing of the order of 0.7% per month. And if you calculate properly, if we keep on the same performance until the end, it is possible to achieve the 25%, which is missing. But installation is much more complicated, and also the COVID-19 has impacted the whole project, and now it is very challenging to keep on to have the first plasma by 2025, as it was decided in 2015. And after we have the first plasma, which will fully demonstrate that we have assembled properly all the main components, we will have what we call a stage approach to the full fusion power capacity, working together with the ITER organization and the ITER members in order to be able to complete the installation. First, it will be to install the way to collect the energy. And after, for example, we will start in December 2028 to offer the possibility to the physicists to have early experience with the tokamak, with the heating system, which will be already installed. And we will have a second phase for assembling the extra heating system, as I mentioned to you, including what we call the neutral beam injectors, which are now to be tested in Italy. And after, we will give again the floor to the scientists from January 2032 to March 2044, before we finally complete the installation with the unit for recycling the fuel, extracting the helium, and we will be ready by 2035 in order to start the full fusion power capacity. So let me now just to give you a few information about where we are. It is an image, as you understand, of the site. You see the very large switchyard, because when we will start, we will need a fraction of a second to have a quite large amount of power to make the electrical discharge. And after that, we will have to convert the power, because we will receive AC power from the European grid, and we need DC power to feed the coils. And so it is the most largest conversion system of AC to DC power in the world. The same, we will need a larger capacity of cryogenics. And so we have the largest cryogenics plant in the world, which will be able to cool down at minus 270 degrees, 25 tons of helium circulating in the coils. And you see in the center of the slide what we call the tokamak complex, with behind this, the assembling hall, where we will be assemble the piece before to put them in the tokamak complex. And last but not the least, we need to be able to cool down the water. The fusion power will have heat up before it will go flow. It will go flow back to the river. So just a few images, I would say. We are very proud that during the main COVID confinement, with the full support of the ITER members and the French government, we have been able to install the base of the cryostat, which is indeed like a cup. The cup is weighing 1,250 tons, 30-meter diameters, and we have been able to put it in what we call the bioprotection cylinder, with a very high precision, which is below 3 millimeter tolerance. It is really, from my point of view, a major engineering achievement. Also, because the cryostat is like a can with a bottom and some cylinder, we will put on the other. This is now achieved. We have been able in August 2020, to assemble the what we call lower cylinder with the base in the tokamak pit, as well as some other equipment. And you see it's very spectacular how you could move now with a big crane, which is able to lift off up to 1,500 tons and be able to proceed. So we are very rewarded by the performance of the industry, which has been able to demonstrate the full capacity to this development. And I am pleased to say that Korea is using the insight learned from manufacturing the thermal shield, which protects the coil from the high temperature of the plasma, to improve, for example, shipping container for liquefied natural gas. So there is always spin-off coming from the innovation on a large international research project. So we are now preparing to install the magnets, the coils, and early 2021 we have been able to weld the base with of the cryostat with the lower cylinder, and it's absolutely remarkable that the workers has been able to weld these two pieces, which are nearly 6 centimeters thick, without any leak, which will be very important for the project. We have also installed what we call the first horizontal magnet in April 2021. It has been procured by Europe, made partly in China, and so you see it is now very well positioned. It is 10-meter diameters, but we will have a much larger one, which I will show you. Also, we have the first sector of the vacuum vessel, which has been positioned for pre-assembly. This vacuum vessel sector, it is one of the 9 sectors, as you know, some quarter of an orange. Each of them is 20-meter high and 450 tons, and it has to be very precisely positioned. And I am pleased that very, very recently, indeed it is yesterday, we have been able to start the assembling of this vacuum vessel sector with the coils. Not only the tokamak is progressing quite well, but also all the auxiliary equipment and facilities, for example, the cryogenic, which is quite impressive, with a lot of compressors, and also all the cryoline, which will allow nearly 20 tons of liquid helium to circulate to cool down, as I said, the ITER magnet to minus 270 degrees and making them superconducting. Also, quite high performance for the electrical network. We are now connected since January 2019 to the European grid, and we have developed very specific equipment in such a way that there is no impact of the ITER needs when we will use this big impulse to start the plasma on the European grid. The magnet power conversion, as I explained to you, is really something which is challenging in order to be able to convert this 70,000 ampere of electrical power from AC to DC. And you see all this equipment coming from many different ITER members, China, India, Korea, and Russia, are being progressively installed inside the magnet power conversion building successfully. Heat rejection is also quite a challenge, and we have been quite innovative indeed. The secondary cooling system will flow through a huge basin with nearly 25,000 cubic meter water in order to have a pre-cooling system before you go with some aero refrigerant system. So it's again quite innovative, and we will try to demonstrate that it is a way to go in the future for power plant, whatever they are in. All the large equipment, as I explained, are coming from the different ITER members. And so they go through the sea mainly due to their size. They arrive at the Marseille harbor, and we have needed to have a special itinerary for the transportation of the highly large equipment, which is 100 kilometers long, and in 3 nights we are able to transport all this large equipment, which could be as large as 10 meters, okay, and weight up to 900 tons. On the site, we are now finalizing some of the fabrication, and you see, for example, the coils, which are 17 meter diameter and 24 meter diameters, made by Europe, is on their way to be completed very soon. And it is really impressive to see the progress that the European industry has been able to demonstrate in order to make this a first-of-a-kind equipment without any equivalent in the world so far. Another important fabrication is a famous cryostat. We have now the base in place. We have also the lower cylinder, the upper cylinder, which are ready. And now it is a top lid, which is maybe most challenging because it is not a simple geometrical lines, but the Indian, jointly with some German company, has been able to comply with the requirement. Europe also is fabricating quite a large number of coils, as you see, as well as some part of the vacuum vessel. And you see on the slide, the worker is equipped with a special suit in order to prevent himself from the COVID. Even during the COVID, everybody has been working, certainly at a reduced speed, but we could not afford to have a delay for these deliveries of the vacuum vessel. Russia, also Japan, they are procuring some equipment, and you see they are quite advanced. Very recently, for example, Japan has provided the 4th coils ready to be shipped very soon from Toshiba, and the other one was from Mitsubishi. All the big companies are involved in. Also, I explained the procurement from India of the cooling water system, and from Korea about some of the vacuum vessel sector. 9 vacuum vessels are to be done, and 5 is from Europe and 4 are from Korea. And China also and the US are delivering very large pieces, very challenging. And for example, very soon the US will be able to provide us with the 7 module of the central solenoid, which is quite an achievement, and we expect that the shipping will start from Texas during this summer. Don't forget, ITER is a project, but it is a unique facility, and worldwide, many others try to contribute to the development of fusion is under development. I already mentioned the joint European Torus, which is still going on, and we expect that it will be able to make a new campaign for the deuterium-tritium demonstration. It will be very important for the ITER project. In Europe also, there is another brand of fusion facility, which is called Stellarrators. It is in Germany, and it is under the supervision of the Max Planck Institute for Plasma Physics. So the magnetic line has to be twisted in order to confine the plasma, and there is 2 ways to twist the line. There is a way ITER is doing it with the central solenoid, and there is another way to twist the coils, but it is quite challenging. But we see also some smaller projects. Very recently, for example, the MIT has been able to gather some partner in order to demonstrate if it is possible to have a more, smaller, more tighter devices in order to demonstrate the steadily of the fusion. And also the tokamak energy is a project in the United Kingdom which demonstrates clearly that there is main interest for fusion. So what is the way forward? I do believe that once ITER will have demonstrated the feasibility, scientific, technological feasibility of fusion, the large utility in the world will consider this technology, and they will make what we call a demonstrators, okay, in such a way that this will have a continuous production of energy. At ITER, it will be some campaign, but it will not try to be connected to the grid. And so based on the lesson learned from ITER, okay, we will expect that a pilot fusion power plant will be developed in the years 2050, something like this. So already some ITER members are pursuing their own pilot plant, including Europe on this matter. We see also private industries beginning to invest in fusion energy initiative in order maybe to improve the way the ITER tokamak will be able to function in the future. And we expect that fusion power plant may be connected to the grid in Europe by 2060, something like this. So we don't believe there is not so many options. If we want to reduce our consumption of fossil fuel with a world population of 8 to 10 billion of inhabitants, we need to rely on the natural phenomena, which is solar energy, either collecting directly the solar radiation arriving on Earth, as we do now with big innovative technologies, but we don't believe it will be sufficient in order to fulfill the energy need for the world energy supply, and is why we believe that the conjunction of fusion energy with renewable will be the viable option. I am pleased with this slide. I'm sure you understand what it is. When I arrived on the site in 2015, I was in my office in front of the work site, and I see in the middle of the afternoon the sky to become very gray. And so I took my cell phone and tried to take a photo of the sky. And suddenly we see that a thunderstorm come in, and I see a natural plasma. Okay, clearly it is not a self-confined plasma, but it indicates to me that maybe we have selected the right place in order to develop, okay, a fully controlled plasma. So thank you very much for your attention. It was my pleasure to introduce you to the ITER fusion, and I hope I was clear enough in order to introduce you to this quite challenging project.
Thank you very much, Bernard. Thank you for having explained to us what you are doing in the site of Cadarache and with whom. I think that you have attracted quite a number of different questions from our audience, so I would jump immediately in the question and answers session with your permission. Because you know, we have a very varied and distinguished audience that ranges from the technical to the political, going through the financial world and so on. So I will try and pick out a few of the questions that we have received in order to stimulate some of your answers. Let me start with one which I think is at the very heart of the mind of some people, and you know, we have assisted in the past few years to a rather spectacular and very fast advancement of the use and deployment of renewable energy, and you are telling us that you know, in 2060. We will have the first fusion plant connected to the European grid. I mean, why should we wait for that?
We will be so pleased to be able to deliver a clear fusion demonstration by next year. But I guess you understand that it is quite challenging to assemble all these components, which are first of a kind. We need time. High quality is really requested. It will be a pity if we are manufacturing all these components and we are not able to make it functioning and as it is expected. So from my point of view, the hydrogen fusion will be a so large breakthrough that it is worth to be patient. And why it is still useful to have fusion? I just addressed this issue a little bit during my presentation. Now, we are developing the renewable energy. We will develop it, but I don't believe with a world population of nearly 10 billion of inhabitants, it will be appropriate, to the need of the world population. We need, as I say, massive, predictable energy. And precisely, the renewable energy are not massive, they are diffuse, and they are not predictable. So with continuity if needed. So we will have a transition, clearly. And I do believe that the transition will be able to develop something which will not be sustainable. And it is precisely around the year 2060 that we will need something replacing the transition system we will have set up from now to the future.
Slightly different, but I think a little bit on the same type of vein. One of our guests is asking, what are the costs up to 2021? You already explained, that each member contributes 9%, with the exception of Europe that contributes 45%. And the other question is, how much further costs are expected?
It's a quite difficult question because, as I explained to you, the 7 members are providing us most of the component in kind. And if I know from the European budget what is the contribution from Europe, if I know from the US budget, it's a little bit more difficult to know from some other ITER members. And including, it's difficult to be sure that we could have a full equivalency of the working cost, working force cost in India, in China, and maybe in California. So the best estimate from my point of view, based on the fact that, for example, Europe is contributing 45%, the US for contributing 9%. I do believe that so far, we have spent altogether around 15 billion euro with all the contract which has been already passed and the cost of installation. And my expectation is before we complete fully the construction, including up to 2035 with all the complementary equipment I mentioned, it will be of the order of 6 to 7 extra billion for the full construction. So my expectation is we will be in the range of 22 billion euro for the full construction. But again, it is not an accounting, because I have no possibility to do that.
And then, if we have such costs, what do you think will be the cost of electricity produced by a machine like ITER?
Okay, so you have to understand that now the cost is certainly not the cost of the fusion power plant. Why? Because there is this complexity with the 7 members. For example, I just want to take an illustration. The vacuum vessel, 5 of the components are made in Europe, 4 are made in Korea. So I have to qualify the 2 suppliers. I have to follow with full quality control both of them. I have to transport from the different countries. And even I am very frank with you, at the beginning, everybody decided to go his way, while it would have been much better to have an integration. So from my point of view, I do believe that the cost of the electricity will be more or less equivalent to the cost of we have now for the fission power plant when they are well amortized. It will be competitive, I do believe, with the cost of the other energy when it will come on the market. And based on the big advantage he has, as I said to you, no impact on the climate and on the environment. So no indirect impact, which will be quite worth. But it is too early to make it very, very evident.
Thank you very much. You showed in one of the slides the different machines, and one of those was the MIT machine Spark. And in the fusion world, there has been for the last decades, very big discussion between, the large, let me call them low-field tokamaks like ITER, and the very compact, very high magnetic field tokamaks like Spark. What is your view on this? Why should we go one way or the other, or is it worth exploring both ways? And to what extent?
First of all,
Red weather alert, please stay in. Alerte orage rouge, ne pas sortir.
Okay, we are.
Red weather alert, please stay in. Alerte orage rouge, ne pas sortir.
You understand that we are on the ITER site and we have an alert of thunderstorm, so it will be moving.
So you are going to have plasma.
Yes, a nice plasma again. So your question is very well said. I do believe that there is a different goal. The goal of ITER is to be able to demonstrate that we will have a net large yield of fusion power, 10 times more than the heat you feed in the fusion. The MIT project Spark don't expect that. What they want to do is to be able to demonstrate a steady state at a much lower yield. So from my point of view, the lesson learned from the two projects will be quite good. Second, the MIT project is relying on the fact that they have discovered at the level of the laboratory some superconducting material which offer a much larger magnetic field, maybe 5 or 10 times more. And so they want to test this material. I could tell you that it takes time to develop usually a new material. And from my point of view, there is some challenge if they succeed, because you understand that if you make things more compact, with the same power, you will have a power flux on the wall, which will be much larger. So you will have what we call a material issue. So from my point of view, I am very pleased that we see all this private, in some way, initiative, because demonstrating that people feel more and more that fusion power could be a real option, and they want to explore on any optimization. So from my point of view, it's clear. Either they will succeed, and I will be so pleased if we could have a much smaller, much more compact system delivering high level of energy. And if they don't fully succeed, we will have a lot of lesson learned. From my physicist background, as I explained to you, I feel that if the plasma volume is too small, it will be nearly impossible to have a high yield of energy.
Okay, let me ask you another question that comes from at least two people plus me, because I happen to work on fusion for quite some part of my working life. And the first time, I will put it in my own words. I will not use the words of the people who have asked the questions, if you allow me. But the first time I read about nuclear fusion, it was in 1972-73, and I was, let me say, 10 years old. And what was written in the little booklet that I was reading is that in 50 years we will have fusion devices delivering this unlimited source of energy to humanity and so on. Here we are in 2021. And what you tell us is that in rather optimistic scenario, you expect the first machine delivering electricity to be connected to the grid in 2060. how should we take these two statements?
Okay, as I mentioned to you, and you are right, hydrogen fusion is so promising that people dream it could become very real very soon. And in the years to 1950, 1960, it was mainly physicists dreaming that they will be able to overcome the challenge. But they forget about the size. And so when the engineers come in and they realize that the plasma will never be stable if you have not a minimum size, okay, people was much more realistic. Now comes the issue. The issue is if you have a very large size, you need a very large collaboration. And it takes time. As I explained to you, it was in 1985 when President Reagan and Secretary Gorbachev launched the program. We had to have a large coalition, including with Europe, Japan, okay, Russia, and the US. And maybe if I would say, Massimo, I am not sure that all these countries are always on the same page on any issue in the world. So it was quite a challenge to make these people working all together, reaching an agreement that the design was the best one, okay, with the right size, and after that to negotiate. So it takes time. And I am as frustrated as yourself and attendance that the 50 years going ahead has been overestimated. Now, sincerely, if the ITER members keep on working together based on the design we have, with all the information we got since the years, I would say 1980, when some real tokamak has been able to demonstrate that fusion power is a reality, I guess that our estimate is quite reliable now.
Thank you. Now, you spoke about renewables as being intermittent sources, but also ITER is a pulsed machine. So when you said that you have this plasma for a certain time, you showed in your slides the amount of time, 500 seconds, whatever it is. So when you look at this, how flexible will be the electricity production out of a machine of this sort?
So it is important that you mention this point. As it is now, in order to get the highest yield, with the design we have, we need to work with pulse, okay? 400 seconds, it is nearly a few minutes. But the good point is that you are ready to restart as soon as you would like after this, if everything is working well. Because as I said to you, it is just in order to twist the magnetic line with the central solenoid. And in order to do that, you have to increase the magnetic field from 0 to the top. And when you are at the top, you need to go down and back again. If you are not so required about the yield, you could have a fully sustained, steady plasma for hours or even days and months, but with a reduced yield, which will be of the order of 5 to 3. So my expectation is that after we have demonstrated the maximum yield, and again, the physics say that the yield could be as high as 40, it is precisely what ITER will try to demonstrate, that we could increase this yield, and second, also, that we could move on a much more longer steady state. So from my point of view, it is nothing to see with the intermediacy of the solar energy. As you know, the night is maybe 8 hours or something like this. And even the power is not always shining. So from my point of view, it is really complementary.
So if we go to reactors size, do you expect that the reactor size, the final reactor, I'm not talking about ITER, I'm talking about devices that will produce electricity, Do you expect the reactor size to be similar or to go through some optimization and decrease in size?
The fact that the fusion power is safe, no risk of runaway or loss of control of the machine, my expectation is that we need to build, we have the possibility to build a much more powerful tokamak system than the one we have. We will produce 500 megawatt of heat. I expect we will be able to produce up to 3,000 megawatt of heat. So it will be certainly larger, but not multiplied by 6. Maybe at the most it will be double size, and we hope that we will be able to have a lot of optimization in such a way that the size will not be as large as just a few minutes ago.
And now I change from one subject to the other a little bit because I think that, as I said, we have such different interests. I think I see a question which I find very attractive. So if we look at the risks that you have on your plate in terms of impact for schedule and budget, that is a worry of many of us, me included. What do you see? Political risk, geopolitical risk, technological risk, financial risk? What do you think is going to be the biggest potential one?
The risk to miss the target, from my point of view, is the assembling of the vacuum vessel sectors and the coils. As I said to you, these pieces are nearly 20 meters high, weighing hundreds of tons. They have to be welded all together with a very high precision. From the point of view of technological risk, I believe it is the most larger one. What pleased me is that the first vacuum vessel sectors, it takes nearly 10 years to the best company in the world to make it, to manufacture it, has been absolutely on requirement. It's really amazing that they have been able, with a precision which is millimetric, to adjust it. And we hope they will fit all together.
No, sorry, go on.
No. The second risk is clearly the political risk. If the ITER members just decide not to go on until the end, clearly the project will stop. Because without the support of the ITER members, not only the financial support, but the industrial support, the intellectual support, okay, because the people which are able to operate this facility to take the best of the experience are spread all over the world. It's not a single country which will be able to afford all the intellectual and scientific resources to go. What makes me a little bit optimistic about this political risk, as you mentioned, is I do believe all the 7 members know that they need an alternate option to the fossil fuel to complement the renewable energies. And there is, for the time being, no other option. So it makes them understanding that there is no other option to keep united and go until the very end. I do believe that all the decision makers, the political leaders, understand that if there is an option which is offering so large advantage, they have no right to miss it. And so I am quite confident, based on these needs, that the political risk is reduced, but it is still there. Because if I would say, I am a physicist, I am maybe a too much rational person, and sometimes in politics it's not exactly the same.
So let me go back to your technological risk, because paradoxically you have attracted and scared some of our audience because you need this absolutely extreme precision to mount your component, and then you will get an earthquake. So what happens to your machine?
Okay, it's a very good point. Indeed, the machine has been built in a special building, which is positioned on a very large slab, 120 meter long, 80 meter large, 1.5 meter thick of a very heavy concrete, which are the slab positioned with nearly 500 anti-seismic pads. So it's precisely because we have assembled this equipment with so high precision that we are able to sustain any large, I would say, earthquake. In France, where we are now in Provence, it was some earthquake in the past, not so large as the one it has been known, as you know, for example, in Japan or in some other part of the world. But so we believe that it is part of the demonstration. We want this equipment to be installed everywhere in the world, as well in California, as maybe in Italy or Japan, where there is some earthquake, which is well known. And so is why we need to do that. So the design has been precisely considering this risk, that there is a way to amortize any vibration coming from the earthquake, or maybe coming also just from big trucks on the road.
Let's go back to electricity production, because I think that there are a number of questions that I'm getting on this, and I think it's interesting to look at it. We are moving to a network which is going to be more and more decentralized, and you tell us, you are building a big machine with a large input power. So how will it fit the network, and will we be able to use the same network and transmission facilities that we have now, in your view?
Yes, absolutely. From my point of view, we could plug in the same network as it is now in order to connect with the fusion power plant. No difficulty. My view is the following. Renewable energy, usually, they are producing locally in many areas, and we need to use as much as we can locally this energy to build a very large network collecting all this energy. So we have to try to develop as much as we can local storage, local production, local consumption. So is why I said the two are complementary, and from my point of view, my answer is crystal clear. No change to the grid, no change on the network to deliver the power. We will have, maybe, if we consider as it is in France, we have something as around 50 nuclear power plant, and we will be able to have maybe half of them, because we will be maybe nearly doubling the power, and the renewable energy will contribute also, and they could be distributed on the territory using the network as it is now. No change. Contrary to what's happened with the renewable energy, where you have to set up the network to collect the energy.
In the conventional nuclear world, there is lots of talk about small modular reactors. What would put ITER at an advantage of these smaller reactors that many people say will be, more versatile, more safe, and will solve some of the issues that you have mentioned?
I know quite well the small modular reactor, as you know, the fission, not fusion, fission, Fission. The advantage, if they are smaller, the risk of runaway is more limited. And you could make it maybe a little bit more compact and confined in such a way that the risk of radioactive release is much limited. But there is two limitations, if I would say so. First of all, you still produce radioactive waste, which will last for very long. So you have to manage, okay, this. And second, you will have not a large amount of raw material, nuclear material. Uranium now, as it is now, with nearly 500 nuclear power plants, we feel that it produces of the order of, I would say, 6–7% of the world energy supply. And if we are just doubling, okay, this, we will have to reduce the lifetime of the raw material availability. And now the raw material availability as it is now is of the order for natural uranium of the order of a few centuries. And so if we are just relying on the SMR, on the long term, it will not fly. It is a good option for the transition. I do believe it's worth to help. As I explained to you, the fusion nuclear power plant, the hydrogen fusion power plant, will come by 2060. So until then, it is time for the SMR to be developed. And after that, I do believe the advantage of the fusion power will be enough in order to overcome the challenge of the management of the radioactive waste coming from the SMR, as well as any of the fission plant.
We have a very kind audience, and you will understand why. Somebody is asking if you would get more financial, industrial, intellectual support, how much could you speed up the project?
I am very pleased to have this question. Quite often it is the type of question I receive. To be frank with you, yes, certainly if we have a little bit more money, it will be able to speed up because we will maybe be able to make some manufacturing in parallel. But as I explained to you, the very high requirement for quality, for a first of a kind, required a clear attention. So from my point of view, for example, as I explained to you, for the first of a kind of the vacuum vessel, it takes 10 years. Now for the second, it takes 20% less time. We will improve. And so if we are speeding up in order to get the best of the learning curves, we will reduce maybe...
Red weather alert over.
Okay.
Alerte orage rouge terminé.
No more alert. Okay.
Red
good.
weather alert over. Alerte orage rouge terminé.
Okay. Sorry for the disturbance. So my expectation, if you, okay, give me doubling the annual income from the project, we could reduce maybe by a factor of, I would say 3 to 5 years, but not more, not more.
Okay, now I ask you the opposite question, if I may, because I think it's important, you know, to hear the replies to the different point of views. So if we put all this money in ITER, aren't we depriving other energy sectors to develop faster than fusion? And is it reasonable to do so?
This is a question everybody has to ask. When you invest some money, is it the best value? I don't believe there is a silver bullet. As I explained to you, fusion power is a complex technology which required high advanced capacity. And I don't see why we will eliminate the option to develop, for example, the renewable energies. For the transition, for example, improving the fission plant, there is not a single way. It will be, from my point of view, a dramatic error to believe that just invest in one technology and it will make it all. We have to accept a mix. We have to accept some possibility to make various of this technology working together. So from my point of view, don't deprive any of the support for energy development. There is some technology that I am not so keen about. To be frank with you, for example, I don't believe that the capture and sequestration of the CO2 is a long-term technology. It could be good for a transition, but it is not a long-term technology. But as far as you develop nuclear technology for the transition, as well as the renewable energies, with storage, with system management of the grid, I do believe it's the right investment.
Okay, I will ask you, I think, 2 more questions, Bernard, and then I will leave you in peace. But I think they are both very, very, very interesting. The first one is what you have explained to us is that this is another type of project that is restricted to high capex type investment. So will, let me say, the owners of these facilities of the future be, the large utilities at the end of the day? Is this the only model that you foresee, or do you see other types of economic development for the commercialization of fusion?
Definitively, as I explained, size matters, and it is complex technology. So I do believe that it should be quite large company able to develop these technologies. What is important to understand is that all the know-how, all the intellectual property development associated to the ITER will be largely available and distributed to any country which want to use these technologies. But for the economical development, when I see the need for high quality control and also able to operate in the very requiring condition, I don't believe it will be a small company able to deliver this type of equipment.
Okay, I think I want to ask you the last question because I find it fascinating. It's a very simple question. And what if it doesn't work, ITER?
What if it does not work?
Yeah.
Is what you say.
Yes. You build all this thing and then it doesn't work.
It will be a terrible deception, certainly. I am a researcher. I do believe if you do things right, and maybe if you don't do it right for the first time, you are able to fix it, you learn of any experience. From my point of view, fusion phenomena is a well-known phenomena. Okay, many tokamak has been built in the world, and nearly 100 of them, and they have not experienced the production of the fusion phenomena. My expectation is why we work so hard, and is why I explained to you that it is not easy to speed up. We want to make it right for the first time. And I do believe with the development of new technologies, for example, the modeling, the simulation, the metrology, we are able to do now what was not possible to do before. Could you imagine, for example, that we have been able to put one over the other, 2 circles, 30-meter diameters, made of a steel, very rigid steel, with a precision of below, half a centimeter. It will never been able before, and I do believe we are now quite controlling the whole process. So your question is, it will create some nightmare for me tonight, but I am quite confident that with the intelligence, the wisdom of all the ITER members, we are now representing more than 50% of the world population, 85% of the GDP. I guess we have all the best assets to be successful. But to conclude, I remember very well when I come in, I visited the US. And I met with the main advisor for the President of the United States, and he questioned me exactly the same as you, and what is the chance to succeed? And I say, we do our best to do that. And he told me, Monsieur Bigot, I don't know if we will use fusion sooner or later, but I want to know if it works or not. And this research project is precisely to answer this question, and we expect that we will be able to provide the positive answer.
Thank you very much, Bernard, and thank you very much for having been so open, to all sorts of questions that our audience has posed. Thank you for the presentation that you have given to us. We will, I think, make the slides available to the participants with your agreement, and I think that this is a project on which Europe has invested a lot. We are fully committed to the success. The European Union has allocated a budget of 5.6 billion euro in the current now financial period 21 to 27 to this project. So I think that the full intellectual, technological and political support to this project is something which we should wish for Bernard and his team. Thank you very much to everybody for the lively participation. Thank you.
Thank you very much, Massimo. It's a challenge to build ITER. It was a challenge also to present to a so large audience, with a large diversity of perspective and maybe background, the ITER project, and I hope I contribute.
Thank you again. Thank you.
Thank you.
Good evening to everybody.
Good evening.